All right, well, happy Monday, everybody. Third week Monday. Yeah, I hope things are going. Does anybody have a midterm already in like third week or something? Not yet, right? Okay, so I think, but we'll have a midterm next week, fourth week. I was like, oh man, this is like so soon already. I was kind of caught off guard myself. But I'll make sure to spend some time going over what you can expect for the midterm during fourth week. So um, we'll go with that. Okay. All right. So just want to kind of follow up a little bit more on regularization. Oh, you can. I will also post your second homework assignment that will be coming soon. So you can expect that either tonight or tomorrow. And I'll also make sure you guys have plenty of time to complete that as well. Okay. I wanted to talk a little bit more about regularization and then just talk about just the general idea of the bias variance trade-off. In our textbook, bias variance trade-off gets maybe like 1 page of mention, which I guess is sufficient, but certainly I think there's a lot more to it. And so I want to talk a little bit about it, even if I'm going to introduce kind of like a model that we don't really use. It's just for illustration, but here, just a quick review. Fill in the blanks in your head, I guess. Okay, so the regularized loss function combines the OLS loss function with blank, and that's like a multi-word answer there. And then the second thing, the blank term is used to determine which goal has greater priority. So just fill in the blanks in your head. All right. Okay. And so what do you guys think? So the answers are the regularized loss function combines the OLS loss function along with a penalty for complexity. All right. And we have kind of different ways to measure complexity. You have the L1 norm, which is the lasso, and you have the L2 norm, which will be ridge regression. Okay. And then the lambda term, which is basically a positive coefficient, is used to determine which goal has greater priority. All right, and so basically, this is a review of what we saw on Friday, and the regularized loss, which we call L prime, is equal to the OLS loss, L being the mean squared error, or it could be the sum of squared error. It doesn't really matter because the mean squared error and sum of squared error are the same thing, just differentiated by some constant, okay, n, pretty much. And then plus lambda times some penalty for complexity, right? And the lasso uses the L1 norm, which is the sum of the absolute values of the coefficients of, in your vector W as the measure of complexity, whereas ridge regression uses the L2 norm squared, so the sum of the squared values and the coefficients as our measure for complexity. There is technically maybe another option. It's called elastic net. Elastic net is like a hybrid between lasso and ridge regression. So if you can't really make up your mind, and if you can't decide like, I want to do L1 norm, use the L1 norm or use the L2 norm as a measure of complexity, you can use elastic net. And elastic net uses a value alpha. Alpha is a number between 0 and 1. And basically, so the measure of complexity is going to be this. So, it's still the regularized loss L prime is still the OLS loss L plus lambda times some complexity parameter. But this time the complexity parameter is going to be a mix between the L1 norm times alpha plus 1 minus the L2 norm times 1 minus alpha. Sorry, 1 minus alpha times the L2 norm. Now this is just for reasons, this is going to be 1 minus alpha over 2, but that's what we have here. Okay, so and so if alpha is equal to 1, pretty much it becomes lasso, and when alpha is equal to 0, it becomes ridge regression. And you can kind of, there's a package in R called glmnet for elastic net, and there's a little bit of a explanation in this PDF here. Okay, just kind of throwing it out there. And so, kind of just what happens here is this is taken straight from the vignette. It says it's known that the ridge regression penalty shrinks the coefficient of correlated predictors towards each other, right? And what that means is kind of the predictors end up having coefficients that are kind of similar to each other. And we saw that a little bit on Friday when I had the line at, the coefficient for W1 and W2 was this diagonal line. And we saw the coefficients, that blue dot kind of approach that line where W1 equals W2 before it starts shrinking, okay? So they tend to kind of push the coefficients towards each other, while lasso tends to pick one of them and discard the others. And we saw that on Friday when we saw that blue dot kind of head towards, it's moving in a diagonal line, and it hits one of the axes when W2 became 0, and we only had a coefficient for W1, and then it moves, and then that one moved towards 0. Okay, so the elastic net penalty kind of mixes the two. If the predictors are correlated in groups, then maybe an alpha of around 0.5 will kind of tend to select the groups in or out together, so that you might have a set of parameters that are set of predictor variables that are similar to each other, and they kind of might, the entire group might get pushed down to 0, or the entire group, might remain. Okay, and so this is kind of what happens, and it's there's not a whole lot of guidance for a lot of these things. It's a lot of kind of guess and check, and see what happens and see what kind of models result, and if the results kind of make sense, right? So the higher level parameter, users might try to pick a value up front or experiment. And experiment just means, you try something out, and if you like it, you can go with it. And if you don't, use something else, okay? And so, lasso tends to push coefficients down to 0. It can be used for variable selection as far as, helping you decide on what kind of model you want. All right, we have a question that says, what are some of the cases where we would prefer elastic net over the other two? Yeah, again, maybe if you have a lot of coefficients, and perhaps, so again, the difference, these are all methods that can be used as far as shrinkage and variance reduction, right? And so all of these things, you're going to get basically biased estimates, in that, OLS, the ordinary least squares coefficients, I guess in the long run, behave well. They're going to be unbiased. But, if problems that we run into, like, why don't we just use OLS all the time? Problems that we run into with OLS is that if you have high collinearity between your predictors, there's a lot of variance as far as, the coefficients. So for example, if you were trying to create a linear regression model for housing data, I don't know, is that maybe in like 101A, a couple of years ago, that you used to use like this big housing data set, and you'd have to like try to figure out your coefficients. And so, some of the variables are highly correlated, right? Like the number, like the square footage, and you might have like multiple square footage variables. You got like livable square footage and total square footage, which includes like the basement and attics and I don't know, whatever else. And you have like the number of bedrooms and the number of bathrooms, and these all things kind of correlate together. And which one's going to be the most predictive. And depending on the data set, one might say, oh, you know what, livable square footage, that's the most important variable. And then another data set, just because of the selection of random data points that you have in it, it might come out and say, you know what, the coefficient for livable square footage is actually low, but just total square footage is the most important thing, right? And that's just a problem that exists with high collinearity, is that you kind of have these things. And so, what lasso and ridge try to do is it tries to reduce the amount of variation that you get, that can result from just having, these highly correlated variables. And Ridge tries to control that by just, rather than allowing any one variable to become like really small and one variable to become really big, it just says, you know what, let's kind of push all of these variables to be similar in size. Lasso, on the other hand, just says, you know what, let's just kind of shrink some of these things. And if some of these things hit 0, so be it, just throw that variable out. Okay. ElasticNet is a little bit of a blend, and it says, you know what, let's try to group some of these variables. And I'm not exactly sure how this grouping things goes together, but like it's going to say like these variables are correlated, and it might kind of push those correlated ones together, and some of the grouped variables might get pushed down to 0. Kind of. In practice, it's not always as beautiful as what this paragraph makes it out to be. And so a lot of times it's just kind of playing around and seeing, using cross-validation, which of these models tends to have good predictive performance. And there's a little bit of an unfortunate side effect of all of these things, is that we start to, as we abstract a little bit more, we lose a little bit of this kind of familiarity and almost like intimate understanding of the variables. And it's more so like, let's just keep trying different things until we get good predictive performance. Whereas with linear regression, you get hopefully a lot of your variables you can make sense of. And so something like housing data, like these variables kind of make sense, and you can reason about them and say, you know what, if I were shopping for a house or a place to, an apartment to live in, I want to see the square footage, right? Or I want to see these kinds of things. And these are variables that we understand. But, there's a lot of data sets where, some of these columns of data are like computer generated and it's difficult for us to even reason with in the first place. And then now we're applying these methods, and the goal is just like, how well are we predicting, and kind of and we're just driven greatly by cross-validation as a way to kind of measure our predictive performance. And so so we do that, and now we're just saying, all right, we're able to reason a little bit less, and we're just kind of turning the cranks and adjusting the knobs to see, like, maybe this will work. Maybe I should try alpha 0.5. Maybe I should try alpha 0.7 and see how that performs. And it kind of comes down to that, with cross-validation as kind of the guiding tool as far as like this is actually performing better. And we're hoping to avoid overfitting by using cross-validation. I have mixed emotions about it. It seems to be the it seems to be the method that's being used very commonly, but at the expense of we're thinking and understanding the data even less and less in certain cases. Anyway, that's that's beside the point. Did I already give you your first view quiz answer? I can't remember. Not yet. Okay. First view quiz answer is the letter A. Letter A as in apple. First view quiz answer for week 3, Monday. The letter A. A as in apple. So we'll do that. Okay. So ElasticNet has been implemented using the package glmnet. And I have to confess, I don't regularly use glmnet very frequently, so I'm only like marginally familiar with some of these commands and stuff. Okay, but so glmnet implements ElasticNet, and that basically implements lasso and ridge regression, because you can just choose alpha equal to 1 or alpha equal to 0 if you wanted lasso, or if you wanted ridge regression. Okay, and so basically, to use glmnet, you've got your matrix X of predictor, your matrix Y of the outcomes, okay, or T. The default is alpha equal to 1, which will be lasso. And as the lambda increases, lasso is going to push some of these coefficients to 0, right? So that's how we have. All right, and so here I just made some artificial data. And inside my X matrix, I've got 4 variables. So when you use glmnet, it's going to give you a whole bunch of lambdas to try out. Okay, it's going to give you, it'll tell you like, these are the results when lambda was this, these are the results when lambda was this. Okay, and so x1 and x2 are highly correlated, x3 and x4 are also highly correlated. Okay, and x1 is independent of x3 and x4, and x2 is also independent of x3 and x4. Okay, and then the values of y in the population depend only on x1 and x3. Okay, so this is a bit contrived, but it's kind of just like, you know, if you think about housing things, you know, you got like maybe the driving force is square footage, or maybe the driving force is the number of bedrooms. Square footage and bedrooms are going to be correlated. Okay, and then maybe you get something else, which is like, I don't know, another driving force is like the median cost of other homes in the neighborhood, kind of like, is this in a nice neighborhood or expensive neighborhood, or I don't know, whatever else, some other statistic that might be related to that. You know, maybe like the local school rating or something. You know, it's unfortunate the way our schools are set up, but just like schools in areas with expensive houses end up having higher school ratings and stuff. So anyway, so, you know, what's the driving force? And so really, as far as the true y, you know, when I generate the true y, I have it related to x1 and I have it related to x3. x2 and x4 play no role in determining the true y, but we're going to add some random noise here, and we're going to try to estimate what y is based on all 4 variables, x1, x2, x3, x4. Okay, and so here we're going to fit glmnet between x and y, and we got lasso because we're using alpha equal to 1, and this is the output. Okay, it says, you know, if you use a lambda of 3 and stuff like this, you're going to end up with 0 coefficients being predicted. And if you, as you decrease your lambda to something smaller and smaller, it's going to include more and more coefficients as part of it. Okay, and so the degrees of freedom will increase, and it says, you know, you've now explained this percentage of the variance of y. Okay, so if you have a lambda equal to this, you know, now you've explained 90.7% of the variance or something, percent deviation. Okay, and so, you know, the results are shown as a listing with 3 columns. First column is the degrees of freedom spent in this model versus the empty model, right? So every additional parameter that you estimate uses up a degree of freedom. Okay, and so effectively, you know, how many variables are being used in the model, and then, you know, the SS regression divided by SS total is going to be the percent of deviation explained, and that's what this is, and it's pretty much equivalent to your R squared value. Okay, and then and then the last column is kind of the value of the lambda term used by glmnet, right? And so when lambda is large, model complexity is punished greatly, and so effectively when you have a big lambda, it pushes your coefficients down to 0, right? And so now we've explained none of the variance, or none of the SS total. Our SS regression is 0, and then as lambda decreases, models are punished less for complexity, meaning it allows the coefficients to get bigger and bigger. And that's what we have, okay? So if we just kind of, if you just fit regular old LM to this, and you ask for the summary, it correctly picks out that x1 and x2 are the correct terms. Okay, it correctly picks those out, and it finds, you know, these are not significant. Okay, and the coefficients here are x1 uses 3 and x3 is negative 1.84 as far as the coefficients go. Okay, whereas when I drew in the true y, it is 3 times x1 and negative 1.8 times x3. Okay. So why does it say R squared is point? Wait, where do you see that? 0.5836, top of the slide. Oh, that's a typo. I don't know why. Okay, that's me messed up. Okay, I messed that up. It should be 0.954. I apologize. Good catch there. That's a mistake. Okay, so we got 0.954 here. So yeah, sorry. I don't know where I drew that. Okay, slide 13, note to self. Okay, and then, so, when lambda is 0, how much are we able to kind of explain? We're going to be able to explain around 95.954. So this is effectively the same as the OLS estimates. And then as we increase lambda inside glmnet, okay, so as we increase the lambda in glmnet, okay, as this gets bigger, the amount that we can explain gets smaller and smaller, right? And so this is kind of where there's a drop off. And at this point, this is a linear drop off because we've gotten down to one coefficient here at like 2 point something. So at 2 point something, we basically get down to one coefficient. And then so that's the only thing, and it gets shrunk down kind of at a linear rate. Is there a way to iterate through alpha values similar to the way it iterates to the lambda values? I don't know if there's a way off the top of my head. Yeah, I mean, you might be able to build your own kind of loop or something to do something like that. But off the top of my head, I'm not sure. But then again, disclaimer, I don't use glmnet all that often to start with. So there might be a feature and I'm just not aware of it either. So, okay, so anyway, this is it. And, you kind of look at this and you just say, well, at what point, how much am I still able to explain and how much reduction am I getting as far as, am I able to get down to say, so in this case, I think we only have like 2 coefficients. And so effectively, we want to just probably, even though these are insignificant, we probably want to choose a lambda where these are just going to get pushed to 0 anyway, which probably is not going to be a very big value, right? And so you can kind of see here, so all of the coefficients are stored in this matrix called beta. Okay, it's technically a sparse matrix, meaning that if it's the value 0, it just gets filled in with dots. Whereas you can take the beta matrix and you can say as dot matrix, and that's going to force all of these dots to get replaced with a 0. So these things are identical, and they get filled with 0. And as pretty much the columns here represent the corresponding coefficients to each line here. So each of these lines, so the first column will correspond to this line in the lasso output, and then the second column will correspond to this line in the lasso output. So the first one is where everything is a 0, and then the second column is where you have 0.273685, which is not a very good model, but it corresponds to this one where we were able to explain like 11%. Okay, and so this goes on for however many rows this has, and I think there's a lot, and they get output here. So if I take kind of the tail, we're going to get up to S55, and even with lasso, this has pushed. There's even the kind of the smallest values here. There's a little bit of penalty, and so it kind of pushed the x2 and x4 coefficients down to 0, right? And it did apply a little bit of shrinkage to the coefficients for variables 1 and 3, okay? Because if you compare it to the OLS coefficients, the coefficient for x1 is a little bit smaller. There's a tiny bit of shrinkage here. And if you compare it to the coefficient for, x3, there's also a tiny bit of shrinkage here as well, okay? Not a ton, but a little bit, okay? And so that's probably, something around 0.054 got, we shrunk all of these by a little bit, or I'm not exactly sure how much, but we applied a little bit of shrinkage. And so effectively the coefficients for variables 2 and 4 were pushed down to 0. And so this would be kind of the results for lasso as far as this. And we could just say, all right, we'll go ahead and use these coefficients. And that's that. Okay. Or you could just say, you know what, take your classical OLS approach and just fit a new model with variables x2 and x4 removed. If you want to see the coefficients for a particular value of lambda, you can specify it and you can say, you know what, I want to find out for s equal to 0.2. I want to figure out for s equal to 1 and stuff, and you'll get different values, right? And so as we use larger values of lambda, the coefficients themselves shrink a bit, okay? And that's what we have. Okay. What happens if a specific lambda value wasn't used? Can you still kind of see that? Oh, yeah, I'm not entirely sure how glmnet uses, how it figures out like what iterations it uses for these lambda values. So I don't know off the top of my head, like if I put in like 0.37, like what is it going to result in? And I don't know. I don't think how significant of a difference it would make though. But sorry, I don't know the answer to that. Okay. glmnet. So glmnet does a lot of the work for you, and you can perform cross-validation with glmnet. Okay. And I don't know if you can see, but there's like this tiny little gray line, vertical gray line here around -3, and a tiny little gray line around -1 point something here. It's very faint. Okay. If you created it on your own, you might be able to see it. Okay. And basically, GLM will automatically do cross-validation, and it'll create some train test splits in the data, and you can create a plot of the results. Okay. And the results will show that, when there's when lambda is big, okay, the mean squared error is huge, okay, and on the other hand, with picking a small lambda, it will actually so here, what this is showing a plot of is that this one on the left is the lowest value, okay? And technically these values are just a tiny bit higher than this value. So this one is the minimum value achieved as far as the cross-validation error, okay? And then it puts some error bars. Let me see. Okay, it puts error bars on this dot here. So technically, so there's like, it's very, very difficult to see in this plot here. And I don't know if I can just zoom in. Okay. So technically this dot is a tiny bit higher than this dot. Okay. It's like impossible to tell in this plot here. Okay. And then there's also these tiny little error bars. Okay. Right. It's got these big error bars, and I forget exactly how I estimated these things. Okay. And so anyway, it says, well, if I go one error bar, one standard error above the center of this red dot, it takes me to this thing. Okay. And then it says, well, what's the biggest value of lambda? Okay. And it's technically log lambda that's getting plotted here. Okay. It says, what's the biggest value of lambda that I can use where I'm still within one standard error of the red dot? Okay. And it says, okay, the biggest value of lambda that you can use, or log lambda that you could use, is technically this one over here. That's this dotted line. Okay. And so kind of the answer of, I don't really want to like reason through, I don't want to think too hard and just give me like an automatic choice here. Like if you use glmnet, the choice will be, okay, use whatever lambda corresponds to this thing, log lambda being -1 point something, like 1.2 or 1.3. And this is going to be basically the largest value of lambda where the mean squared error is within one standard error of the minimum mean squared error that was achieved via cross-validation, if that kind of makes sense, right? So it says, what's the smallest mean squared error that we achieved? It's this thing. But, this value over here, which uses a larger lambda, its mean squared error is a little bit higher, but it's not that different. It's like within one standard error of the lowest one. And so we could probably use this one over here, which is a bigger one, which might be a more desirable choice. And it's kind of just as good, right? Maybe. And so I kind of, I think I've explained that here. So the lambda.min is the value of lambda that produced the smallest cross-validation mean squared error. Okay, the cross-validation mean squared error has a standard error because it is subject to random train test splits. And so the smallest cross-validation error may not be significantly different from another cross-validation error that's slightly larger. And so the lambda.1 SE value is a larger value of lambda that still produced a small cross-validation error. Even if it's not the smallest one, it is within one standard error of the minimum cross-validation error that was produced. And so if you don't want to think too hard, or this is kind of like your default recommendation is lambda.1 SE, right? But you, as the person designing models and making choices, you can choose whether you want to go with this default recommended value or if you have better reasoning through it, okay? Okay, so anyway, let's talk a little bit about regularization stuff. And, I'm wasting too much time talking here. Let me give you your second view quiz answer. Second view quiz answer is D, D as in dog. D as in dog is your second view quiz answer today. D as in dog. All right. And so, the idea here is that, when you fit a model to your observed data, we have to always keep in mind that the observed data we have is subject to just random noise, right? There's random noise in the observed data, and therefore the coefficients are subject to that. And then they might not be the best ones because there could have been a lot of things, right? And so, if we had taken another random sample from the population, and we probably don't have this luxury in real life, but if we did, we would probably get similar but different coefficient estimates, right? And OLS, ordinary least squares regression, these are going to produce your best linear unbiased estimators. And I think you probably had to prove this in 100B as well, or 100C or something. You say, this is the best. And in this case, best means, is that they have the minimum amount of variance among all possible kind of coefficient estimates that would be unbiased, right? Unbiased meaning like in the long run, the expected value of these estimators are going to be equal to the true values in the population. That's what it means to be unbiased. And these are the best because it has the lowest amount of variance among possible unbiased estimators, right? But as we talked about, if certain variables are highly correlated, those coefficients will exhibit high variance. And so what, lasso and ridge regression and this whole idea of regularization is it's trying to reduce the variance, right? And it's saying, we're going to reduce the variance at the expense of introducing bias. We're no longer going to have estimators where the expected value is exactly equal to the true values, but they're going to be a little bit off, so they're biased. But we're okay with that because the amount of variance that results is lower, and I guess, in our case, this is a desirable trait, right? So that's what it says, right? Having less variance in the coefficients is a desirable trait of models. And so that means, the models that we estimate are less likely to be swayed by the kind of the random noise that exists in the observed data. And, if you have a model where the coefficients are changing drastically from one random sample to another random sample, then your estimates that you have right now, you're not going to be super confident in them, right? Because you're saying, well, if I had a slightly different random sample, my coefficient estimates could be, all over the place. So I'm not quite sure how I feel about these coefficients right now. Right? And that's just kind of, yeah, that's all of life, right? You just say, well, I'm not quite sure how I feel because I've only, been to this restaurant twice or something, if you have a consistent experience after, hundreds of visits, you go, oh, okay, all right, you know, In-N-Out Burger is a good place. But after, you know, whatever, yeah, what, now I don't know where I'm going here. Okay, but so anyway, I just have some simulated slides here that show kind of just what lasso and ridge regression will produce, you know, coefficient estimates that lower the variance, but they're going to introduce bias here, right? Okay, so the true relationship, once again, we've got 4 variables, x1, x2, x3, and x4. The true relationship is just based on x1 and x3, and the true coefficients are 3 and negative 1.8, right? And in all of these things, I'm going to just add a whole bunch of random noise, okay? And we're going to fit OLS, we're going to fit lasso, we're going to fit ridge regression, okay? And for lasso and ridge, we're going to go ahead and use GLM's cross-validation, and I'm just going to pick the largest lambda that's within 1 standard error, and we're just going to use that, okay? So again, I'm not going to think about this. I'm going to just say, all right, glmnet, I did lasso, glmnet, I do ridge. Tell me what numbers I should use according to getting the best ones that are within 1 standard error of the minimum. And let's just see what coefficients we end up getting, okay? And so this is kind of the loop of code that I'm going to run. I do all of this stuff. All right, and so this is what we get, okay? So up here, this is the distribution of the coefficient for x1 if the true coefficient is 3, okay? So the true coefficient is 3, and we look at OLS, and we go, oh yeah, you know, the OLS model, it's centered at 3, okay? But it goes anywhere from, what is this, 2.2 to 3.7 or 3.8, something around there, okay? You look at the ones for lasso, and they are not centered at 3. They're centered at 2.65-ish, okay? They're biased. The center of the estimates for lasso is much lower, but then you look at the amount of variance, and I would say it's less, right? The amount of spread here, we go from 2.2 to 3.2, okay? Whereas over here, we went from 2.2 to say 3.8. So there's definitely more variance here. Here, this is a smaller range, less variance, okay? Here, again, with ridge, our coefficient is, I would say, a lot more biased, at estimated at like maybe 2.25, but also the amount of variance is a lot lower, at like from 1.8 to 2.8, okay? So we've got lower variance here, but definitely bias in that the center here is no longer at 3. Okay. Is that all right? As far as what we have. So if we look at OLS, the mean OLS is, you know, 3. And if you look at the variance of the OLS, we have 0.06. If we look at lasso, the mean is off 2.68 rather than 3, but the variance is less at 0.03. Oh, it got cut off. Okay. The mean over here is 2.26, biased. The variance here is a smaller number than 0.06. I don't know off the top of my head, it got cut off here. Okay, if you look at x2, this is kind of where you start to see some of the big differences here. Okay, with the x2 coefficient, okay, with ordinary least squares regression, yes, it's centered at 0. The true value for x2 is 0. With OLS, it's centered at 0. But we got quite a bit of variance. When anywhere from -1 to like 0.5. With lasso, what it's doing is it's just kind of sliding everything down, and when it basically hits 0, it stops. Okay, so we're centered at 0, maybe a little bit off, and but basically it's not going to do anything. Ridge regression, we're biased, okay, because it doesn't like having anything way off from anything else. So we have very few values that are at 0. It's actually biased to be much higher, okay? But the amount of variance that we have. So with the OLS, the variance is around 0.08. The center is around 0. Variance is around 0.087, okay? With lasso, the center is still close to 0, 0.022. But the variance is much smaller, 0.0087 versus 0.087. So the variance is, you know, 1/10. And again, over here, it's off. The variance here is actually not small. It's not really an improvement, okay? Or maybe just smaller variance but significantly biased here. All right, so those are just some properties, just looking at the results of the coefficients by fitting the same model a whole bunch of times to different random samples of the data. Okay, let me see if I can whip through this bias variance trade-off kind of quickly. I know I've got like 10 minutes to get through 30 slides here, but I think I can do it. Okay, basically bias squared plus variance plus sigma squared, where sigma squared is the standard deviation of the noise in the generating data. Okay, bias is basically how much your expected value for the coefficient is off from the true value in the population. Okay, that's the difference between I'm sorry, not the coefficient, the predicted value and the actual value. Variance is the variance of kind of the predicted values, this term's variance, and sigma is the standard deviation of the noise in the generating data. Okay, this slide is about lowest regression. Have you guys learned about localized regression? Lowest regression, local regression? Okay, so blah, 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 blah. That's a great explanation of a slide. But basically, the true model is this, okay? The true model is going to be this quadratic curve, okay? True model is this quadratic curve. All right, and someone said, no, we didn't learn about localized regression. Okay, it's all right. There's not much to worry about, okay? The true model is this quadratic curve. And what I'm going to do is we're going to try fitting a few models here, okay? And so here, these dots represent random data points centered around the true model, okay? So the true model is this dotted red line, but if you add random noise, sometimes you get points that are bigger, sometimes you get points that are smaller. And so here I just say, here, give me some points, add some random noise around here, okay? And here I'm going to try fitting a straight line to these dots, and this is the resulting line that gets fit. I say, all right, what if I had another random sample of data drawn, centered at the same red line, but again, because of random noise, I get slightly different dots. Okay, so over here I had these dots centered around this. This time I got these dots centered around the red line. Okay, and I'm fitting a straight line to these dots. And I do this with one more. Okay, these are another random set of dots, and I'm fitting a straight line. So if I compare all three, because we had different dots, our fitted lines are similar, but not exactly the same. Okay. And so the point here, when we talk about bias and variance, the variance is how much does this fitted line vary from this fitted line from this fitted line, right? So each of the fitted lines vary from each other. And how much variance is there? Well, there's a little bit of variance, but overall, I would say these fitted lines are kind of similar to each other, okay? And so I'm going to do this a whole bunch of times. Oh, not yet. I'm getting ahead of myself, okay? So we say, all right, how much variance is there from one fit to another? And there's a bit of variance, but overall, these lines are kind of similar to each other, right? And the reason why they're different is because each of the random dots that we drew from the population differ from each other. Okay. Here I'm going to do the same thing, but I'm going to fit a low-S curve. Okay, and a low-S curve basically says try to fit like a squiggly line, a smoothed out squiggly line to your dots. Okay, and there's a parameter in low-S where you say, I want you to do a really good job fitting the dots. I don't mind if it's really squiggly. Or you can say, I want it to be pretty smooth, and I don't mind if you miss the dots, right? And so that's kind of this term here, span. You change the span in low-S, and it's going to either fit a really squiggly line, or it's going to try to fit something smoother, right? And you can kind of adjust this, right? And the point here being really squiggly is going to overfit, and really smooth is not. Really squiggly will have low bias, high variance. Really smooth will have high bias, low variance. Okay, so this is low bias, high variance. Okay, and that we're going to fit these dots very well, okay? And so another set of random dots and another set of random dots. And if I compare all three lines, okay, compare the lowest models to different samples, we're gonna say, how much do these fitted lines vary from each other? And I'd say quite a bit, right? These lines, you know, for this point, this one's predicting way down here and this one's predicting way up here. And, you know, for this one's predicting up here and this one's predicting down here. So we have quite a bit of variance from one lowest line to another. Okay, so what we see here are models that do a very good job of fitting their observed data. There's these lines do a very good job of fitting the observed data. And if you average all of these, if you took the average of all three lines, it would probably be very close to this dotted line, okay? But if you look at one model compared to another, they're going to differ quite drastically from each other, right? Okay, so this is just taking this to the extreme, all right, where I just do this a whole bunch of times. I'm going to fit linear models a whole bunch of times, and I'm going to just plot them all on. And then I'm going to do the other one, the squiggly line, a whole bunch of times and plot them all. Okay, and I've written them all down in the slides, and so you can take the time to read through them, and I've commented all of my code that I used to do this. Okay, but basically this, all of these lines, it looks like kind of like a bundle of rainbow spaghetti, is just all of these straight lines are fit to a bunch of different random points that are centered around the true line, which is this quadratic line. Okay, but and they fit this, right? And so if you average this, these white dots represent the average of the fitted values. Okay, and if you look at one line to another, you know, they're not exactly the same. They exhibit some variance, but overall, the lines are quite similar to each other. Okay, so we'd say there's low variance between one fitted line to another, low variance. Okay, but as far as the predicted lines, like what's the average of all of these things, they're kind of far off from the true value. Okay, the true value over is, you know, right here on this. Now it's black, the true curve, and there's quite a bit of variance between, or bias between this dot and the true predicted value. Okay, there's quite a bit of variance. Okay, on the other hand, so the white dots do not fit the true relationship well. That's high bias. The different colored straight lines do not vary drastically from each other. That's low variance. Okay, so black line is the true relationship in the population. The different colored straight lines represent all of the different linear models that were fit, and the white dots represent the average of the predicted values from these different linear models. Okay, this is all of the low S. Okay, and so we have a bunch of like, this is like tangled rainbow hair. Okay, and it's kind of all crazy, right? And again, the black line in dark is the true relationship. The white dots are the average of the fitted lines. And each of these spaghetti rainbow lines are is the squiggly low S curve. Okay, the squiggly low S curve is are each of these things. Okay, so the average, like if I average all of these different squiggled lines, I get this white dot. Okay, and if I average all of these squiggled lines, I get this white dot. Okay, and so we could see these white dots fit the true relationship, which is the black line, pretty well. Okay, yeah, they're not exactly in line with the light, right? This one's a little bit lower and this one's a little bit higher, but overall the white dots fit the true line fairly decently, I would say. Okay, but as far as how one line varies to another, they're all over the place, right? There's high variance from one squiggle line to another. Okay, and so that's what it means to have low bias, in that in the long run, if you fit a whole bunch of these things, the average of your prediction is going to be close to the true value. That's what the low bias is. Okay, is that the average of your predictions across different models will be close to the true value. But from one model to another, there's a high amount of variance. So if you only have one model, you don't know if you're close to the true value or not. Okay, and so that's what we have. The white dots fit the true relationship very well, in that we have low bias if you average all of your fitted values. but the different colored dots vary drastically from each other. And so you have high variance from one fitted line to another. And again, in practice, you're only looking at one and you're like, well, I don't know if this is any good. So ideally, you want something that's like a little bit of a balance here. And so this was achieved with lowest by kind of just fiddling with the terms, okay? And so here we're hoping, so this is something where, the bias seems pretty low, like the average fits the true relationship quite well, okay? And how much do the lines vary from each other? Overall, I would say the lines, there's variance from one model to another, but the amount of variance seems to be a lot less, okay? So hopefully we're getting some kind of balance between these two, which is what we want to achieve, okay? And so, I skipped over a lot of the technical code. I didn't explain my code, and you can kind of read through my explanations a little bit. But overall, when we talk about bias, we're talking about if you averaged all of your predictions over many repetitions, would the average be close to the true value? Okay, let's end there. Let me give you your last view quiz answer. Last view quiz answer today is E as an elephant. E as an elephant is your last view quiz answer for today. Okay. All right, we'll end there. So have a good evening, and you can expect homework 2 to get posted, and we will see you guys on Wednesday.